All right, good morning, everybody. Welcome to day 4 of 2023 HFIP annual meeting. Thank you for persevering through these long days. Appreciate it. We obviously aren't going to go as long today because a lot of people are traveling out. Hopefully, we don't have to worry about anybody having issues with shutdown stuff. So today, our first session is talking about developer and developer support and HPC, and then a couple of other add-on topics. I'm going to hand it over to Will Kamarami to chair this session. Thank you.
All right, thanks for that, Aaron. For our first presenter, I'd like to introduce Catherine Newman, who's going to be discussing DTC support transition out. Take it away, Catherine.
All right, great, thanks. Can you hear me all right?
Yep.
Okay. Well, good morning. It's an early one here in Colorado. First, I wanted to express that I'm disappointed not to be there in person this week. It was a difficult week for me to travel, but regardless, it's been a really great meeting, and even attending remotely. So kudos to those who are executing this hybrid event. It's been really great. So I'll jump right in. I'm Catherine Newman from NCAR and the DTC. And the talk that I've been asked to give is Developmental Center, Testbed Center Transition, Support Transition Out. So next slide, please. All right, so given that this talk is sort of a handoff of our longstanding support activities, I wanted to acknowledge the full DTC team throughout the years as represented in the slide, rather than just the current contributors as co-authors. And additionally, I wanted to acknowledge that our efforts were nothing without the great community and collaborators that we've worked with over the years. So I attempted to list the various institutions that we've been fortunate enough to work with, and I would say that first and foremost is NOAA EMC, who have been close collaborators for all of these activities. Next slide, please. Okay, so quick outline of my talk. I've heard a few times this week that this is the first HFIP meeting for some folks, so I wanted to quickly cover the DTC for context. And then next, I thought it'd be a little fun to recap a few highlights from our hurricane software and support activities throughout the years. And then I'll give an update on the status of our HAFS support and our transition to EPIC. And then finally, I'll end with some ongoing and future activities in the DTC as it pertains to HAFS. So next slide, please. All right, so what is the DTC? The DTC is a partnership between NOAA, the U.S. Air Force, and NCAR. And for the activities in this presentation, we're covering NOAA-funded activities. Our mission is to bridge research and operations to accelerate improvements in Earth system understanding and prediction by advancing collaborative model testing and evaluation and developing indispensable community assessment tools. The graphic on the right shows the 3 main areas that we work in: community software support, testing and evaluation, and community interactions, which includes the DTC visitor program that I'll discuss within this presentation. And then going back up to the community software support, this is an area where we've historically been very involved, but over the past few years, we've been sunsetting and transitioning some of our software systems to EPIC, with HAFS being the final handoff. We will continue to work in this area of community software support with the systems that we develop and support internally, which are the Enhanced Model Evaluation Tools, or MET+, and the Common Community Physics Package, or CCPP. Next slide, please. All right, so I thought I'd spend a few slides focusing on some highlights from our DTC hurricane software support. The strategies that we employed for operations to research to operations were to support operational NWP systems to the community, partner with developers to get innovations into the centralized code, and to perform diagnostics and testing and evaluation on promising NWP innovations for possible operational implementation. To meet this, we were engaged in code management, public releases and tutorials, user and developer support, community engagement, and testing and evaluation. So next slide. All right, so the first slide highlight is our HWRF and GFDL Vortex Tracker releases. So we released HWRF on an annual cadence following each operational implementation, and the release versions included the operational capabilities plus some additional research capabilities. It was well-tested, stable code that included extensive documentation. We also had a standalone GFDL Vortex Tracker that was released in collaboration with Tim Marchak, and this allowed users to be able to run the Vortex Tracker on model output other than HWRF. The key message that I wanted to deliver here is that the DTC is undergoing a website update. And with that, we are looking to sunset materials from our legacy systems, and both of these systems fall under that. So this means that all community support content for these systems, documentation, training, data sets, etc., will be removed from the dtcenter.org in spring of 2024. We're targeting April. And so I just wanted to let everyone know we'll be posting announcements to the web and alerting mailing list, but this is advanced warning that you may want to download any materials that you wish to keep over the next couple months. Next slide, please. All right, so following each public release, we held in-person tutorials that were covering the new public release. And here I pulled up a few group photos from some of these events, both held domestically and internationally. And I'm sure if you look close, you can probably see yourselves in some of these pictures. A couple memories that come to mind when I look at these events. The bottom right is actually our very first unexpected hybrid training event, well in advance of COVID. This tutorial fell during the January 2016 nor'easter blizzard event that shut down flights into the Mid-Atlantic, and we ended up hosting the tutorial both online and in person for the 3-day event. And then in the lower left in 2018, this actually occurred on the heels of a government shutdown. This one was a shorter one. It was only a few days, but the government opened back up on Monday evening, and we managed to be up and running first thing Tuesday morning in the NCWCP. So big thanks to everyone that helped out with that. And needless to say, there was many contingency plans that didn't end up getting executed. So I think the moral of the story here is that the more things change, the more things seem to stay the same. And finally, I have a note here similar to the last slide that training and tutorial materials will be pulled down this coming spring. So be sure to grab them if you wish to. All right, next slide. Okay, so the final highlight that I'm going to show is pertaining to our research to operations. So we were able to work with the community developers to facilitate innovations, making it into 6 different operational implementations of HWRF. And one key area where we made these connections was through our visitor program. And we've had a slew of great visitor projects that had various impacts, but the ones listed on the table directly impacted operations. And so this work includes work back to 2013 with Rich Jablonski with POM TC, efforts to advance the 2015 HWRF implementation by Rob Favell focused on both radiation and PBL parameterizations. And then there were 2 rounds of innovations pertaining to the cloud overlap scheme from Mike Iacono and John Henderson. Other efforts outside of the visitor program included working with Greg Thompson, who worked with us directly to develop a partial cloudiness scheme within our TMG. All right, next slide. Okay, so now I'm going to move on to the HAFS support. The overarching motivation for these activities is that strong governance and developer support leads to a more rapid transition of research developments into operations and ultimately improves HAFS forecasts. And so in the next few slides, I'll cover our ongoing HAFS code management and support activities and give an update on the status of the transition to EPIC. Next slide, please. Okay, so starting with code management, we work to ensure clear development protocols are maintained to assure effective distributed development. The DTC is serving as co-code owners of the HAFS community GitHub organization along with EMC. And we also help to maintain the integrity of the code and avoid code divergence through running workflow regression tests on multiple platforms. Additionally, HRF code repository governance is posted to the HAFS community wiki with established protocols and process for development, and content such as code styles for general code and scripting guidance are available. Next slide, please. So for developer support, this support has been available for developers on development, code integration for innovations into the HAFS repository, and code reviews. This is an aspect that we'll be ramping down over the coming months. We encourage developers to attend the HAFS developer community calls to discuss and coordinate development efforts and create GitHub issues describing their development. The DTC is available to help facilitate these efforts in coordination with EPIC. And additionally, we set up GitHub discussions to serve as a space to pose questions or solutions or announcements. GitHub is nice because it provides a single location for all resources, and it's consistent with the other UFS applications. I'll note that the DTC already stepped back from actively monitoring this space due to funding, but recently EPIC has been engaging in this area, and so I've listed this as an effort that's an ongoing activity for transition. Next slide, please. Okay, continuing with developer support, I mentioned that HAFS developer committee meetings. These are held bi-weekly on Mondays at noon Eastern time. These meetings provide a platform for information exchange where code updates and feedback on development efforts are discussed to ensure coordination. And the chairing responsibility recently transitioned from DTC to EPIC last month. Next slide. Finally, the DTC stood up some initial HAFS documentation and read the docs, and this was recently merged into develop. This serves as a quick start guide for those who are beginning to run HAFS. The transition over to EPIC occurred after this merge, and they've been working on expanding this documentation. And the plan is for DTC to continue to engage with EPIC to help build out this documentation over the coming months. Next slide. Okay, I'm actually a little ahead of time here. So the next few slides were meant to give a quick overview of where else DTC is engaging with respect to the HAFS system. This isn't the focus of this talk, but I wanted to provide some context on DTC's role going forward. So yeah, please, next slide. Okay, so first is our testing and evaluation activities. We work to identify promising innovations from the broader research community. This includes the HFIP community and funding PIs from WPO or OSDI, for example. And additionally, we have PIs from the DTC visitor program who have historically been quite successful in bringing in innovations into the operational hurricane systems. And we tend to tap subject matter experts and developers from UFS working groups or from our home institutions to make connections. So next, we assess code readiness and potential for operations in collaboration with EMC. We meet to discuss priorities and areas of opportunity to bring community research innovations. And this helps the community gain visibility for their community contributions. So we plan to continue to work in this area. Currently, we are looking into RFS physics for HAFS with help from some of our GSL colleagues. And finally, we strive to work closely with developers to configure and test these innovations in an iterative testing and evaluation process. We're starting efforts through the UFS R2O project to establish a MET+-based agile testing framework, which would bring MET+ into the HAFS workflow and allow, in particular, community developers to test and evaluate innovations in a rapid and controlled way in order to evaluate against established benchmarks. Next slide, please. So we continue to seek collaborations through our DTC visitor program. We currently have 2 funded HAFS-related projects in progress, which are listed in the table below. The QR code in the upper right brings us to the visitor program site, which has more information on our announcement of opportunity and the type of funding awards that we have available. So if you're interested in working with us, go ahead and check that out. And as I've previously mentioned, we have a history of research funded through the DTC visitor program that's contributing back to HWRF and HAFS development efforts. And so PIs with varying levels of HAFS experience are encouraged. We've had PIs who are active developers and PIs who have yet to run the system. And so we also have graduate student project opportunities available. And so the DTC will provide support in running the system and working with the repository, evaluating forecasts, and navigating the development process. And I just wanted to mention that these efforts are separate from the developer support efforts that are being handed off to EPIC. And so this continues to remain a focus under the DTC support. Next slide, please. All right, so in close, the DTC is currently transitioning its longstanding hurricane code management and support activities to EPIC. The timeline currently is to see support on 30 June 2024. And so this coming up summer. Another important date to keep in mind is the removal of the HWRF and GFDL projects tracker materials from the DTC website, which is planned for this spring. The DTC will continue to engage through testing and evaluation, including diagnostics and T&E using tools such as MET+, employing model hierarchy approaches using tools that are connected to the CCPP, and continuing to make connections through our visitor program. And finally, I just wanted to close by saying thanks. We really enjoyed having the privilege to be in an active role of supporting this community and these modeling systems. It's been really great. And we really look forward to continued collaborations. So with that, I'll close. I guess I'm a few minutes ahead of time, but I guess next up is Maui.
All right. Well, thanks for that, Catherine. Yeah, you finished a little bit early, but I think we'll take that. We usually end up eating into the minutes between the transitions anyway. So I believe I saw Maui Wong on the line. Want to test your mic, Maui?
Can you hear me?
Yep, we can hear you.
Okay, I'll wait a little bit.
Looks like it's loading right now.
Yeah, I have a big picture, that's why.
So after our last talk about DTC transition out, we will have Maui speaking about the EPIC transition in. So with that, take it away, Maui.
Yeah, sure. I really want to thank Catherine and DTC as a whole in this process of transition because their guidance has been very important for us. We actually started with these transition activities with DTC for other UFS applications like 3 years ago. And we have been enjoying this partnership. I'm sure we're going to work together in the future on other things. So Catherine, I'm sure I'm going to see you in the future in this meeting again. But I want to mention that I know that this title is a little different from what's being assigned, but I will explain why I want to present a holistic picture of EPIC before I get to that point of support. Just to begin with, this is a title not created by me. This is a BAMS paper title authored by former NOAA leadership. So this is their mandate or their hope for EPIC to become, right? So I really take that very serious that EPIC is a catalyst for NOAA's future Earth prediction systems. So I'll just present some high-level examples for you so that you understand what that means. Next slide. So this vision and mission statement are actually from that paper as well as from the EPIC strategic plan approved by the Congress in January 2020. In this strategic plan, EPIC's vision is to enable the most accurate and reliable operational numerical forecast model in the world. That mission is very big and cannot be achieved by EPIC alone. So we will need to work as a community to achieve that vision. But within that big vision, EPIC's mission is actually to be the catalyst for the community research and modeling systems advances so that we can continuously inform and the advances in operational forecast modeling system. So this is a very important statement that we need to keep in sync with the research community and the operational community and make sure that our 202R funnel is clarified. Next slide. And based on the strategic plan, this is actually our strategic implementation plan at a very high level. One is that we want to nurture an inclusive and diverse modeling community, as well as to establish an infrastructure that is publicly accessible to enable end-to-end testing and development environment for the unified forecast system. And the third one is that through the community and infrastructure, we need to be able to enable innovations so that we can bring innovations to improve UFS forecast skills and computational performance. Next slide. And so this slide is to show you, because EPIC has proposed is actually a virtual center. We don't have a building or any hard space that will require people to work on. If you have a chance, go into the EPIC web portal, that's epic.noaa.gov. You can see who we are, and we are actually distributed across the country. To begin with, but that portal is not just for the EPIC team itself. The portal is actually to enable the community. So you are going to find the UFS code, and you will be able to get support by looking at those two red circles. And starting from October, EPIC is working with the UFS Communication and Outreach Working Group to publish UFS newspapers. So we're actually soliciting new content. If you have any ideas, please send me a message. And starting from this summer, actually last summer, EPIC actually started working with UCAR community programs to establish the WINGS Fellowship Program. We get our first cohort of WINGS Fellow started in the summer, and they are very, very smart and bright. And You can also find EPIC training content on the website. One example is the upcoming EPIC application training on weather, short-range weather application version 2.2. So if you're interested in looking into that, please sign up. It's totally free. Next slide. And EPIC is also strengthening the community by convening those public workshops. A lot of you probably remember the 2019 EPIC workshop. That is when the EPIC mission and vision was compiled, and we started drafting the strategic plan. And then EPIC went into a 2-year silent period for acquisition. We started the workshops again, but this time it's renamed UIFCW. And in 2022, and we had another one in 2023. We have been seeing a shift in attendance just between those 2 years. In 2022, it was very NOAA-centric, and in 2023, we got a lot of community members attending, as well as very good discussions across all UFS application teams. And we did realize that areas of improvement, and a lot of you were attending that workshop, and you're more than welcome to provide additional inputs. So we found that we need cross-sector partners as well as to build the capacity for all the teams, right? So so there are other things we need to work on. We have started the planning for the workshop for 2024. As I said, you are more than welcome to provide input from the planning stage. Next slide. So another example is actually the releases. We started working with UFS short-range weather application team, releasing it to the community. The short-range weather SRW is the regional model for near-term and severe weather forecast. So I want to mention this was supported by DTC as well, and then it was transitioned to EPIC in 2022. So we started releasing SRW 2.0, and then transitioned to 2.1 and to 2.2, which was released in October 2023. There are a lot of good features in that release. You might want to explore that include configurable workflow and model grids, CCPP physics suites, and it doesn't only include LUFAS or short-range weather suites. It also includes GFS physics suite. If you want to try the effect of switching physics suites, that's where you want to try. And it includes workflow and end-to-end tests and expansion to UFS test cases. And you can actually find that in the developers branch. And we started working with DTC to integrate Mac and Mac Plus from this version on. And it is portable across all on-premise and cloud HPCs, Linux, Mac operational systems, and also works within a cloud container. Not just cloud, you can just use that container for other purposes. And the UFS air quality model is now part of it, but it's not the most up-to-date version. So it's not currently supported. And we are transitioning to spec stack at this point. I agree. Thanks, Mike. But we didn't include that, right, at this moment in this release, but it's part of it. And so the spec stack is actually one software stack package that would enable both UFS and JEDI, just for your information. We worked with a lot of partners, not just EPIC, so that's why the partner list is very long. We start to using alphabetic order in order to provide that acknowledgement. If you're interested, just click on the links and you can find more information. Next slide. Okay, so this one is just to dive into a little bit more details. The short-range weather application is not the only one application that EPIC is supporting at this moment. We're supporting the short-range weather application by providing the user's guide and a wiki page that include the developer's guide. And similarly, EPIC is supporting a land data assimilation system right now. You can find similar support mechanisms there. UFS weather model, which is a forecast model for all UFS applications, is also supported by EPIC and with partnership with EMC. So for whatever development into UFS weather model, you should be able to find support there as well. And the unified post-processor, which is also a UFS component, is also supported by EPIC at this moment. And you can find technical FAQs on the EPIC webpage, which provide, that could be your starting point because maybe other people have asked questions before. And for user support, right now we are using GitHub discussions as a mechanism to get your questions. So if you click on those links, you can find where to ask questions. Next slide. And the other thing that the EPIC team, contract team is working on is to establish the EPIC cloud architecture. We have different purposes, different cloud architecture for different purposes. NOAA internal cloud that includes the parallel works within, supported by NOAA HPC program, as well as AWS supported by OER ACIO. They are both enabled by EPIC to support the EPIC website, continuous integration and continuous deployment, as well as testing and benchmarking. And we also support public sandbox. Right now, the AWS sandbox is enabled. We can use our logging.gov logging for that sandbox. And it is actually supported by OER ACIO. And we are working, so Azure is now supported by Raytheon itself, but once we get that done, we will work with ACIO to see whether we can follow the same safety protocol for that. We're still working on GCP. And starting from the summer, we started releasing cloud infrastructure as software. That means you can actually find a script that will enable you to load all the software stack, libraries, etc., to compile a UFS application on GitHub. Next slide. And as part of this infrastructure, we are enabling testing framework that includes CI/CD, but that's not only it, right? So we are looking at unit test, component test, integration test, and then work with DTC and verification and validation. And we work on model performance to look at how scalable the UFS applications are. We have a tool for code analysis to look into the code quality. And containers, as I mentioned, that's always coming as part of the UFS releases. So these are the tools that are key for UFS community developers. If you come to our training, you are going to get more explanations on those. Next slide. And also, we have enabled other infrastructure on the EPIC web portal that, for example, you can find all UFS GitHub metrics in graphics. On the EPIC website, benchmarking results are also translated to cloud cost estimators. You can also find it on the EPIC website. The CI/CD stats, they are actually now public. You can actually, well, if you're allowed to, if you submit a PR, right? So you can, on the right-hand side, you can see a PR number. If you submit a PR, you can actually follow its status by looking at build time, time per gates, and the average build time, and whether or not you succeed or failed in that CI/CD pipeline. So that's also enabled. And the hierarchical testing framework, I'm sure that Mike will talk about that. We are very happy to have that relationship with DTC to enable both testing and development. And as I mentioned earlier, MapClass-based forecast matrix is now part of the SRW application. You can find it there as well. Next slide. And so I talked about infrastructure and community building for a long time, but essentially we are building this infrastructure to enable innovations. One example here is that starting from last year, we partnered with WAPO programs that include JTTI, fire weather, and S2S programs to solicit innovation proposals toward improve numerical weather prediction capabilities, hydrology, and fire weather. At this moment, we were not able to support all these three targets, but the numerical weather prediction capabilities is a very good example to potentially use EPIC infrastructure toward R2O and 2R. Next slide. Another innovation related to WPO solicitations is the recently closed DA consortium funding opportunity. So we are asking for DA consortium proposals to leverage EPIC infrastructure toward accelerating UFS DA development. You can also find a lot of details there. Another thing I want to mention is that actually EPIC program is providing NOAA-based funding to the Joint Center for Satellite Data Assimilation. So you see a lot of JEDI releases. A large portion of that was supported by the EPIC program. Next slide. So now eventually I'm getting to the HAFS support discussion. Catherine provided a very good background there. So we started that interaction with a HPC program a while ago, maybe half a year ago. So after some discussions, as well as with other UFS application teams, we realized that there is a need for us to step back a little bit to review the overall UFS governance, including software governance, right? So a few very high-level questions for you to consider as a UFS application shall HAFS follow the same principle with all other UFS applications. So we need to work with a team with all other UFS applications to understand what it means. Shall we follow the same infrastructure and code standards? Shall we follow the same developer and user support paradigms? What should be coordinated between the application teams and the supporting teams? And one example of that is who should be deciding whether to release or support UFS components, for example, GSI, right? So these are some very high-level questions we need to consider. But however, we still have some very near-term goals. Catherine provided a very good review on the transition activities. The EPIC contract team right now is focusing on internal release, targeting at HAFS developers, including training, workshop, and documentation. We're going to start that activity from January 2024. DTC is part of this process. We're working closely together. Another thing I want to mention is that in this year, EPIC program also provided funding to GFDL to establish GFDL Vortex Tracker as a properly supported UFS community-based GitHub project. So that means they are going to follow UFS standards, including consolidating all versions across UFS applications and establish CI/CD across tier 1 platforms, doing periodic releases, as well as issue tracking with the UFS community. Next slide. Okay, so this is a very high-level diagram on where EPIC is going. So that's why we're working with the community to make sure we achieve consensus and work together towards the UFS, a joint UFS community modeling infrastructure. So next slide. I want to show my acknowledgement. So we work with a lot of partners, and even under the EPIC contract, we have a lot of private companies, and we work with NOAA centers and labs, including EMC, GSO, PSO, AOML, and GFDL, and a lot of CIs, as well as HPCC NOD program, as well as the private sector commercial cloud service providers. I really want to thank all of you for your support to the HFIP program. I'll just stop here.
Thank you, Maui. Really nice summary there. I see that we continue to run a little bit ahead of schedule, so I'm happy to take credit for that. For our next, and so for our next presentation, we originally had Pablo and Mark D. Maria listed, but it looks like Wallace Hogsett will be giving this next one. So with that, Wallace, take it away.
Whether you like it or not, I'm back. I'll do my best Pablo impression. All right, so I'm going to talk about the next generation wind speed probability model. It's probably the biggest change that will be coming to the wind speed probability model since the model went operational about 20 years ago. So the development has been a big team effort between the Hurricane Center and Mark D. Maria and team out at Sierra. So with that, I will jump in. Okay, so I'm going to talk a little bit about the legacy, just a quick overview of the legacy wind speed probability model to make sure we're on the same page. Then I'll talk about the WTCM, which is effectively the wind model, which will drive the wind speed probability model. And then I'll talk about the new wind speed probability model itself, as well as some of the products that will come out of the wind speed probability model. There'll be some new products. I'll talk a little bit also about some of the downstream implications because the model data itself is used in a lot of different applications. And then I'll talk about the transition plan to operations over the next couple of years. Okay, so the legacy wind speed probability model, it's a statistical Monte Carlo based model with 1,000 realizations. It's been operational since 2006. And I'll talk about some of the changes that have occurred since then. But the track and intensity ensembles are based on climatological, the last 5-year error statistics from the official forecast. There is a weak dependence on track errors in terms of the dynamical models, but it's a very weak dependence, and we're going to be looking to improve this, as I'll talk about. The wind structure perturbations are entirely climatology and persistence radiac clipper based, and so there's no incorporation at all of the forecast errors. When you see the term TCM here, I don't know why we decided to say TCM, but that's the forecast, the official forecast. And then the legacy model also, we produce a suite of products, 34, 50, 64 knot wind probabilities out to 5 days, as well as the time of arrival of 34 knot winds, both the earliest reasonable and the most likely time of arrival. You're probably familiar with most of these products. Okay, I won't read off all of these, but there have been a lot of changes since 2006. Annual updates, of course, to the error distributions to update that 5-year error data set. And then relatively frequently, there are adjustments to the track interpolations, land reduction. Time of arrival was introduced about 5 years ago. And there was an attempt in 2020, Mark can probably elaborate on this, but it was an attempt to incorporate the NHC radii, but that was abandoned due to some issues with time continuity. And we have had a 7-day version. I mentioned the legacy model runs 5 days. We have had a 7-day version running in-house since 2020. The model itself is run in a couple places, and we're hoping to streamline this with version 2. But the model is run on WCOS, the NWS supercomputer, and there's an early run that's run about an hour before advisory time, and then there's the final run that's run immediately after the advisory time. We also run the model locally, and this is used for preliminary graphics as well as the text products and the time of arrival. So it's a little bit complicated. Okay, so before we go to the new wind speed probability model itself, I want to talk about the wind model that is the foundation for the next generation model. So the WTCM, aka the wind model, for the new version is a full 2-dimensional wind field derived from the forecast. So the enhanced version is called WTCM because it's using the same kind of Rankine vortex with wave number 1 asymmetry, but with the forecast parameters from the TCM, the forecast. And the big change, which you'll see propagate down into the output of the model, is the wind reduction over land. So there's a surface layer, or a land surface model with 16 land surface types that you can see it in this animation here, dramatically impacts the wind field when it moves from marine exposure onto land. So over the development of the WTCM, the new wind model, it's been calibrated with ASOS and weather flow observations. I think on the next slide we'll show a picture of kind of where some of these are along the coast as well as inland. It's a 1 kilometer horizontal resolution, 1 hour temporal resolution, and again it's been run in real time internally for evaluation and feedback, and it has been used in some of the grids that are used by produced by WFOs as well as in sub. Some of the upcoming improvements we're looking to include a gust parameterization, adjust for elevation as well, and continue to update the land surface database. Okay, so in terms of the wind model and how it's been validated and calibrated, so there are 19 recent landfalling TCs. And what the team has done is run the WTCM using the best track inputs for all of these TCs, and then match up the observation stations with that best track run of the WTCM. And using the comparisons between the OBS and the model, this is how the team has kind of adjusted the roughness and the reductions for the various land types. So you can see the tracks of these 19 recent storms. And just a little more detail here on the validation and calibration using the observations. Again, 19 storms. Each of the observation types produces a different frequency. So there's some subsampling done to match up the WTCM outputs with the characteristics of the observations. And in total, you can see, tens of thousands of matched points, and you can see a little summary of the error characteristics and the bias here. We can get into a little bit more detail about how this was done, and Mark can probably elaborate a little bit on this. So a recent example of the calibration from 2022 to the 2023 version, you can see here reduction factors for several of the land surface type groups, forest, grasslands, urban, etc. And the bottom line here is that from 2022 to 2023, we reduced the reduction factors, which effectively means we increased the reduction of the winds. So the result from 2022 to 2023 is that there's more wind reduction over land. So you'll see in some of the examples, the difference between the marine and the land is even greater in 2023. And this is a work in progress, the validation calibration. Okay, here are a couple examples. On the left is ELSA, and on the right is a test case of a ridiculously intense tropical cyclone. Perhaps not even realistic, but you can see, just over the marine exposure, you can see a broader swath of winds, and immediately when you get over land, you can see a much finer detail in terms of the wind speeds for the WTCM. You can see things like, stronger winds over Lake Okeechobee. I think I'm losing my battery, but that's okay. But anyhow, dramatic difference between the marine and the land. And we think this is a very realistic, more realistic depiction of the wind speeds. But again, this is you'll see in some of the next slides, this is going to be a significant change. It is one thing I want to mention here also is that the WTCM is always locked onto the official forecast. So. All right, so what are we currently working on? So that was the wind model itself. Now, the wind speed probability model. The plan is to, and we've been doing this experimentally, the plan is to run all 1,000 members with the full two-dimensional wind field. So instead of the Monte Carlo that's based on statistical error characteristics, we're going to run all 1,000 with the new wind model. Again, very detailed land surface information. The legacy wind speed probability model was run at 50-kilometer resolution. And right now we're testing a variety of resolutions. It will definitely be higher than 50. We're testing everything from 20 to 10 to 5. We want to get it as high resolution as possible while fitting within the constraints of the supercomputing environment that we have. And a preliminary version, you can take a look at the link at the very bottom here. A preliminary version of the model has been run and posted on CIRA's real-time website. So you can go back and look at an archive of all cases to get a sense of, with some of the legacy model parameters still in place, you can get a sense of the land surface impacts. And there's a comparison of the legacy model with the new model on the website for all these cases. All right, so what's coming next in the development? We're working on replacing the radii clipper method to perturb the radii with the forecast inputs. The team is also working on replacing the gypsy, so the light dependence on the track or the situational information with some ensemble input, and perhaps replacing some of the climatology-based error distributions with a new machine learning technique that is perhaps somewhat tied to the model that Mark talked about yesterday. Of course, a lot of validation calibration needs to happen. You'll see this in some of the plots I'll show in a second. And we're also coordinating with the PSurge group, because PSurge is critically dependent on RMW, and there might be some consistency benefits by working together to drive PSurge off of something similar to the new WTCM. And then I mentioned earlier that work's underway to add these elevation adjustments and gust parameterizations. Okay, so here's an example. I mentioned that some of the samples were up on the CIRA website. This is an example from Ian on the left-hand side, you can see the legacy wind speed probabilities, and in the center is a run of the wind speed probability 2.0. It's pretty clear what you get in terms of probabilities, a reduction of the probabilities over land. And on the right-hand side is, one of the things we're going to unlock with this new model are a variety of new parameters, probability of 96 knot winds and exceedance probabilities. So from a probabilistic IDSS point of view, communicating the forecast, a product like this could be very useful. So this is a 10% exceedance. Effectively, what we're saying is there's a 10% chance based on the model that winds will exceed the value shown here. You can think of this as like effectively a reasonable worst case scenario, kind of like the surge products that are produced. So from a messaging point of view, this could be a valuable addition to the product suite. All right, so where are we at so far? Obviously, there are large differences over land. We knew this was the case, but part of the reason we've been running and posting the output on CIRA's page is to get people familiar with the characteristics of the new model. And let's see here, what else we got? Yeah, so lots of, we're still working on, how much detail to include. There are some aliasing issues related to the difference between the land surface database itself and the resolution of the model. So we're working to address some of these aliasing issues. And one thing, I'm going to jump here into the downstream applications. One thing we're really working to optimize is how this wind speed probability, new probability data flows into these downstream applications. So I'm going to go ahead and show a few examples of this. So we have an application that was recently baselined. It's going to be fully operational next year, called the Wind Hazard Recommender. And effectively what this tool does is it takes the wind speed probability information and recommends watches and warnings, both along the coast as well as inland, for a variety of hazards, tropical storm, hurricane. And you can see here the difference between the recommended watches and warnings from the legacy model on the left and from the new model on the right. So there are potentially downstream implications here about how watches and warnings would be recommended. You know, whether the recommendations are taken, you know, at face value, we'll see. But we want to make sure that this highlights the validation calibration effort. There's likely going to be a need to continue to calibrate the model to make sure we get the right recommendations for watches and warnings. This is another example. So if you think of someone, like, let's pretend you're in Fort Myers and you open up weather.gov and you look at the forecast, on the left-hand side, you would probably see a message. Actually, I'll just stay here for this. Anything in brown, it would say something like hurricane conditions possible. With the new model, you know, you can see a big difference in terms of the, you know, where that message would be conveyed. So again, in terms of the public messaging resulting from this new model, we want to be really careful about the calibration and the validation. So I think I've said that term like 3 or 4 times. I might say it a couple more times. Big deal. All right, you can just see a couple more examples here. I think the message is pretty clear. The probabilities reduced over land, so a lot of the downstream products and messaging associated with that will also be lower. All right, so in terms, I think I got just a couple more slides. In terms of the transition to operations, our current plan, so I mentioned the WTCM, the wind model, has been run internally for a couple of years. And our plan is to run it on WCOS development system in 2024 and transition to production in 2025. That's for the wind model. And for the wind speed probability model, based on the new wind model, our plan is to run that on the WCOS supercomputer in development next year and in development in 2025 with a target for operational implementation in 2026. So we still got a little ways to go before this becomes operational, but we wanted to kind of highlight what's coming because, like I said, this is the biggest change to the wind speed probability model since it was implemented in 2006. So with that, I'll stop and leave up some of the contacts here. Again, Mark DeMaria and team at Sierra, and Pablo is kind of the lead on the Hurricane Center side, but you can reach out to any of us if you have questions. And I'm sure you have some questions, and I'll stop, and there's a good chance that Mark will be the one to answer some detailed questions, but thank you.
All right, thank you, Wallace. Yeah, that was very interesting to see the impact over land. Pretty stark contrast. So for our next presenter, we have Mike Eck on the line, I believe, to present on physics across scales.
We do. Thank you.
All right, Mike.
I noticed a lot of nice questions in the chat going on. So let me share my window. And
yeah, Mike, we'll go through those questions at the end.
Oh, right. Okay, that's right. I remember the.
And just for reference, some of the questions are being answered in the background by folks that are participants or investigators in some of these talks as well.
Okay. Here we go. Well, let's see. Where did my notes go? Okay, so can everyone see this?
Yes, we can.
Okay, fantastic. So, well, I might be gaining some more time even. This is a rather short talk, and it doesn't focus on HAFS or hurricanes. Rather, it's mostly on the model development process, but certainly that needs to tie in with what hurricane model development is. So in Catherine's talk about the DTC support for hurricane modeling, she noted the hierarchical system development approach for model testing and evaluation. And that was also mentioned in Mao Yu's talk. And for those of you that know me, I like to talk about this process because I think it's very efficient for us to use this approach. I gave such a talk at the UFS workshop, the UIFCW, this summer in Boulder, as usual. And I want to kind of walk through a few of the things that are important here. But physics across scales becomes an important issue, and again, that can relate to hurricanes. So let's see. A rather large list of contributors here on some of the original work on the physics across scales that Catherine Newman led, and then a large cadre of people from DTC that were involved in a lot of the hierarchical system development approach. So anyway, I'll go to my next slide. So for consistent solutions, the use of the hierarchical system development. Let's walk through this. What is hierarchical system development? An efficient model development approach spanning simple to complex with multiple entry points to work more easily with the broad Earth system community. It's not really a mystery. Hierarchical system development has been and is going on. We're just talking about how do we connect these steps to make it efficient. An article is written and it goes into a journal, and then somebody looks at that and goes, I'd like to test in a single column model to, you know, kind of sort out the physics, et cetera, moving all the way up through something that finally goes through an implementation. So I guess the big deal is with R2O, the efficiency by which we get these changes into our models is really is a measure of the success. How long does it take? Specific to this talk, HSD helps in the understanding of the spatial and temporal dependencies in the model physics and the need for the consistency in solutions across different, well, UFS applications. So what you get in a high resolution model, you may not have the details in the coarse resolution, but there needs to be some kind of consistency across these different applications. For example, precipitation in the global model is going to be, of course, on a coarser resolution, but somehow that needs to be reflected for all the grid boxes and subgrid boxes that are actually then being used in or as part of the higher resolution models. So what does HSD leverage? Well, the Common Community Physics Package, which you heard Catherine and you heard Mao Yi talk about, basically it enables HSD via this framework to connect physics and models. So it puts it in a common framework, and then we're able to test it across different applications. MAP Plus supports the diagnostics and verification you'll need as part of this process, many at the process level. That's really important because standard meteorological measures are quite important, of course, but you want to know things like aerosol optical depth, what is the boundary layer depth, what are the surface fluxes, things like that that really go down at the process level. So what does it provide? The simpler versions of a more complex system. It's easier to work with simple parts of the model before you go to the fully complex parts. Testing pathways for updates and new innovations. Easier to test things in a smaller or simpler version. And it's a more efficient use of compute resources. So this cartoon here, essentially, let's see. Can you all see my cursor?
Yes, we can.
Great, thank you very much. Okay, so basically this hierarchy, it's called that because if you look at a model and it's broken down, you can have individual parameterization simulators, then beyond that a single column model, maybe a 2D model, small domain, good for looking at convection in a limited sense, so you don't have to run a large scale model, the regional domain, global model, and then fully coupled model. So there's all of these different testing paradigms that can exist, and we're trying to develop pieces of that. Working at DTC, there's you know, we're trying to cover parts of this, but it's an entire community thing that we need to work on together. I mentioned process level assessments because these need to be done throughout the process. You may not learn you can't learn a whole lot about landfalling hurricanes and strength and intensity by looking at in an individual parameterization for, say, the surface flux, or geez, don't touch it, surface stress or something like that. But you can certainly find something out about a surface flux or maybe a boundary layer depth in the column model and so on. This understanding part here of this diagram essentially says that there's an awful lot of understanding of individual processes in the column model and so on as you march up, but that understanding of the individual processes diminishes as you get to the fully coupled model. On the other hand, you can't understand a whole lot about the systems by just looking at the process simulators or even the single column model. But as you progress down this testing this testing hierarchy, you're learning more and more about the systems. So we need to be looking at all of these things simultaneously, really. But one step can help the other. One simpler step can then help improve things in the more complex steps. But you can find some errors. You can find some errors in the more coupled versions, regional, global, fully coupled, that can then translate down and suggest maybe what do I want to work on a very focused on processes. So finally, this one. Why do we need this? Well, there's many Earth system processes to model, from regional to global. So if you look at interactions, this is over the land. We could equally draw one on the ocean surface processes, but all these things are going on. This isn't conceptual. This is based on, tearing apart land boundary layer and land processes from model parameterizations. But this needs to fit into a very larger regional and global domain. So we're trying to look at all of these things. To understand the model biases, we often need to simplify things, as we talked about previously, and for efficient use of compute. I'll repeat that. Really important. You can do an awful lot of individual parameterization tests for the cost of a fully coupled model. You can do 100,000 single column model runs and maybe learn a lot about the phase space of the behavior of your parameterizations. So really important to do. Just to give you a little background, this comes from the climate community, and where a hierarchical approach was used to understand climate models, their components, and their behavior. There was a nice second model hierarchies workshop in August of 22. The first one was in 2016, as noted here. Tim Palmer, who was at that workshop, the original workshop, said hierarchical thinking should be second nature for all weather and climate scientists. That's nice. Julie Slingo did a review of the World Climate Research Program, and she said we need to increase our focus on process level understanding for model improvement. Focus on process level understanding. Sure, you ultimately end up with a fully coupled model, but you want to understand if you're getting the processes right and connect weather and climate. So this isn't just about climate, it's about weather and climate and connecting the two. Kristen Jakob is probably one of the most strong advocates for hierarchy. He's a WCRP researcher, and he wrote a very nice article in BAMS and another one later in 2014. But in 2010, he pointed out that the community needs to improve the diagnosis of processes contributing to model errors. Where is it going wrong? We really need to dig in, and we need a lot more model developers and not just model users. And he also said that this applies equally to Earth system models used for weather. So I've talked to Christian quite a bit, and he says, oh yeah, transcends weather to climate. So going back to Julia's message, Tim's message. So this HST cycle, you can look at kind of a big loop at this, or an upper loop, where you're looking at, oh, this is just an NCAR example, sorry, but you're looking at, you can apply, this should be applied to the UFS, where you look at the specific models that exist, but you make assessments, and you go back and do system calibration, tuning, if you will, of the whole system. However, if you want to learn more about the processes, if you want to learn more about where you're going wrong, then you have to descend into this full cycle that looks at both the coupled model and then the processes. And there's a smaller lower loop here where you can really focus on the individual processes. So you need to make sure that all of these things are going on. Small processes, the coupled models, the full models, and then connecting those. Really important to do. There's a HST focused article that leverages Kristen Jakob's paper that's on the UFScommunity.org website. Talks about this. So let's go to back to the evaluation of CCPP physics across scales. This is part of that understanding where that scope is. And so I'm just showing a couple of slides where we were trying to look at this. So we wanted to look at the horizontal grid spacing, okay, and we focused on various phenomenon using the UFS, kind of a 3 kilometer convective allowing model, 13 kilometer medium range weather model, and a 25 kilometer S2S grid spacing. And then we used 2 different packages from the GFS and RRFS, and also included some Common Community Physics package single column model simulations. So we were using the regional model to make our tests. So we emphasized this testing approach, and we utilized the single column model, and then physics tendencies we pulled out of CCPP plus MEP+ verification and diagnostics. So we were using the UFS limited area model, so over CONUS and HAFS domains. We're looking at that, noting the different applications we have here. Some of these names are a little more out of date, but they definitely fit into what we're using for like RRFS, SRW, and so on. And we evaluated the ability of the GFS and RRFS physics suites to make forecasts for these 5 diverse weather elements. Hurricane Barry, the track, Hurricane Laura, the precip, severe weather outbreak, a heat wave, and a cold air outbreak. So, you know, looking at a spectrum of things. So the impact of the horizontal grid length on the forecast. So looking at temperature, again, over CONUS domain and looking at what happened, both RRFS, GFS and RRFS physics runs became a bit cooler as the grid spacing was decreased. Important to understand. So this just shows this over that CONUS area for the temperature. Looking at cloud cover, the GFS physics suite runs became cloudier with finer grid space resolution. The RRFS was generally more mixed. Okay, important to understand. Precipitation, several comments here. The 25 and 13 kilometer runs for both physics suites produced similar amounts of precip. The 3 kilometer runs produced 1.5 to 2 times more precip and verified more closely with the observations. Good finding. And in the tropical storm cases, the precipitation was more broadly distributed throughout the storm circulation in the 3 kilometer runs. Finally, looking at hurricane tracks, or the tropical storm cyclone tracks, the forecasts were degraded, improved in the GFS versus the RFS physics suite at finer grid lengths. So there's kind of a mixed bag here. The poor tracks were associated with excessive convection in the northeast quadrant of the storm. So the bottom line from this study was that neither physics suite produced scale invariant results for forecasts of precipitation, cloud cover, precipitation, or a cyclone track. So this is important to know, because if we're using a model, if we're using several different configurations of the UFS, whether it's whether it's seasonal, whether it's global, whether it's regional, or whether it's hurricane, we want to understand what are these differences in physics, because it's nice if we can work together on physics and see where those scales dependencies depend. One more slide about this. We were applying the hierarchical system development approach by looking at, well, can the CCPP single column model be used to study the model performance at different delta X grid spacings? And looking at the UFS LAM versus the CCPP single column model, basically what this is a question is, can we use the single column model to look at model performance by pulling out single column models, pulling out a single column from the UFS and then rerunning. And that's really nice if you want to focus on one area or another area or another area, rather than having to run the whole model. You can look at things in isolation. And yes, using the single column model, we can, in this replay mode, where we grab a column from the UFS, run, and we can see the behavior of what's going on. In this case, we have the observations versus the LAM versus the CCP SCM. So there's that ability to utilize our tools more effectively. So those were just examples of some previous work. Obviously, it's been updated. Thank you, Catherine and company that have worked on that. I'll just close by saying, well, what are these summaries and challenges? Earth system models for weather and climate are becoming increasingly more complex, many processes, interactions, and we need to get the right answers for the right reasons. Hierarchical system development approach is essentially a systems engineering approach where we break it down into small pieces, like physics schemes, and look at them in isolation and then progressively connect all of these things. That doesn't have to be sequential. Actually, you're doing all of these things at the same time, and you can learn something from one step that's more coupled and complex, and you can translate it down into looking at some physics and just really focusing on those small elements and everything in between. It was that systems versus processes hierarchy that we saw previously. So HSD can help improve the understanding of spatial and temporal dependencies. So focusing on those different resolutions and applications. And as I said, this process is concurrent and iterative. These complex steps of the HSD can then yield information on the simpler steps and vice versa. Common community physics package, an efficient way to connect all these things. MET Plus for verification and diagnostics, include process level. And finally, NCAR's Joint Numerical Testbed and DTC are working with EPIC and with the Earth System Research and Modeling Community on the use of AHSD for a more effective model improvement, development improvement process. I guess that's it. Thank you.
Thanks a lot, Mike. Very interesting discussion. I'm sure we'll probably have some questions for you at the end, so if you could just stand by, that would be great. So for our final talk of this session, we have Radhika from our HPC. I don't know if we also have Frank Individuo on the line, if you were planning to tag team.
Frank is on the line. I saw him log in.
But
I'm here, but Radhika's got it.
yeah, I'll have Radhika lead it off then. So there's another mic up there. Yep.
Oh, okay. Oh, this is great. So, hi everyone. Thank you. This is a great opportunity for me to be here and actually meet everybody in person. So thanks for this opportunity, and I hope I can explain to you what we do. And I think I'm going to be following the bottom line upfront method here. So just really cut to the chase, and then I can go in and explain everything out. So next slide, please. The HPC board decision was made in March 2023, so this year, and it received a unanimous vote from all NOAA line offices members. And so the HPC board, for everyone's understanding, the membership is at the line office DAA level. And basically, that's invest in compute expansion at the NESC, which is in Fairmont, instead of at the Boulder location. And basically, it stems from three main reasons. You know, we have the data center there that we can maximize compute and performance, and then it improves the efficiency. Brings scheduling of those milestones ahead of time so that we can provide you compute sooner, and then really positions us for future compute expansion. And I'll go into this a little bit more, but I wanted to say, like, our primary mission of HPC and the R&D HPC specifically is to support NOAA science efforts. So I'm here to support you guys. So with that said, next slide, please. So the reasons, how is this going to work out? How is the expansion going to work out at the NESC? So first of all, there's going to be no change to what we are doing out in Boulder and supporting JET. That's going to continue. So actually, this is probably going to be the very first time that we're not going to turn off anything to start a new thing. We've never been in a position like this before, In the past, whenever we had to do broad scale recapitalizations, we had to turn off systems to turn on new ones. So this is the first case where we are blessed by Congress that we have a lot of funds. So we keep existing contracts, maintenance, everything going on the current systems and actually turn on new systems for you guys. So we do that expansion. Again, there will be no change to on-site personnel. And we are actually going to be investing in JET. So we have contract awarded in JET, where we expect new file system to come in place. And I think that's already been awarded, I think executed. We've purchased the file system. It's going to land soon. And then we are, so JET's going to be available for the hurricane season. Additionally, we've also expanded our cloud offerings. As you're aware, we have, we had a lot of cloud resources that we put in place in 23 and 22 and 21, but really a lot more in 23 that was there to support the HAFS development. And thank you to the team here who's worked really hard to use that resource. And I really appreciate all the work that happened there. And to add on to that, we brought on now subject matter experts because we heard you. We heard you loud and clear that you need experts to help you port. And that's what I heard again and again in all the meetings. So now I have actually brought on 4 new people and trying to bring on a few more subject matter experts that are going to help you to move your models. So the goal is to have, that's the goal, is to have a unified access to all the systems, regardless of, what you're using. So we're planning to have a unified platform across, unified architecture, so that we have a software stack, and then we are just starting to reach that goal. And our first step is to actually not just provide the system side support, but also to help in the middle with the porting to the different platforms as you're bringing on those platforms. Okay, next slide. So the timeline now is winter 2024 to 25. And the reason the timeline is like this is because I have to work with a number of people to bring compute. It doesn't happen like this. I wish things happen like this. Just like the budget process, there is a planning process for this one. This is a capital capital purchase, right? So we go into planning, getting the funds, and then actually I have to work a lot with our procurement shop. I have to work with our facility folks. So I wish things could happen like this, but it takes a while. And then with the supply chain, even though I work with the contracts, I get my contracts in place, I put my task orders in, and then I'm out of the AGO door, but now I'm in the vendor door. So now the vendor has to go out and then they need to call people. They have supply chain issues where they have to bring down those big machines and things like that. So that is a cycle. And once even the system lands, there is still steps that we need to do in terms of making sure your codes run on the machine, right? So there's configuration, validation, testing, pilot users, acceptance of that, and then it goes into general acceptance. So I'm just kind of laying it out there. So that's why we are talking about the winter 2024 to 25. The plan is to install the supplemental system at Fairmont, establish the reservation on the system, make sure it works, right? That's important. Develop a plan for testing of the reservations, and do the user test. And then JET continues, right? There's nothing going wrong there. Everything kind of continues. We're trying on the new system, making sure it works for everybody. Okay, next slide, please. Year 3. All right, you guys can transition over. You've already tested it. You've made sure it works. System's already in general acceptance. No changes to JET, no changes to people and personnel, and the support expands. And then we'll support JET as long as we can find parts for it. All right. I know there are going to be questions later, but next slide. All right, going into the long part of the presentation here, just to explain, we've actually increased our capacity by more than 50%, close to 50% in 1 year. We landed 2 new systems. Gaia is now a 10 petaflop system, used to be 5. That doubled, okay? MSU used to be a 5 petaflop system, now it's 8. Okay, then we have cloud. And that 2 petaflop is just an estimate. We put in several $1 million. I'm trying to work out how the cores and dollars are going to work, but more is coming. And this is what we have right now. And then the top pie chart on the top left shows you who's using it. So I'm happy to say we broke over 1,000 user mark. Thank you to you. We are, I think, 1,010 and growing because of the increase in utilization of the cloud and the new systems and the supplemental projects are getting on the systems. So thank you. All right, next slide. This just kind of goes through that exact thing that I said. So 10 petaflops of compute capacity at Gaia, which would be the Gaia C5. You've still not turned off C4. C4 is available, all right? C3 just got decommissioned. C4, there's a plan to get it decommissioned. So my plan is to make sure everything works in phases. Nothing gets turned off until everybody is moved over. And then that was in production in May 2023. And in June 2023, we brought in Hercules as part of the Orion expansion. And then for the whole year, I think we added $6 million more to the cloud computing to support all the cloud projects. All right, that was just the base funding that we received. Like I told you, we got an onslaught of funds in 22. Next slide, please. This is the disaster supplemental that we received, again in 22. So $50 million was received. We did 2 things with it. One was we sent money over to Oak Ridge, and then that compute is expected to become in production early next year. I'm told, I was at the supercomputing conference yesterday, and I was told that, you know, the system's going to land soon. So I'm very hopeful that once it lands, we go through the cycles of general acceptance and, you know, bring on pilot users, test that system out, and then get that into your hands as soon as possible. Number 2 things that we did was increase the compute capacity at the NESC. For that, I had to work with AGO, all right? And then that's something that the task order is going to get awarded in the spring, okay? Now, that's the task order award. And then it's ordering, bringing the system on, and so on and so forth. That I had mentioned before. All right, next slide. We received $80 million in BIL, FY22. You guys are seeing the trend here. A lot of FY22 actions. So AGO has their hands full in trying to make sure that we are addressed. Again, this is the facility infrastructure at the NESC. So this is going to be my number 3 compute at NESC. So number 1 is Hera, number 2 is the one that I talked about in the previous slide, and number 3 is this one. Number 3 at the NESC for $40 million. The remaining $40 million was spent on improving the infrastructure. And the 3 things that we are doing there to improve the infrastructure is increase the power, because you guys know supercomputers drink a lot of power. Need to make sure that the pipes are big enough to bring in that electrical capacity. So it's going up to 8 megawatts, and we're working on that with GSA. I had a meeting with GSA as well last week, November 9th. And basically it was Ben Friedman spoke at the summit, as well as the GSA regional commissioner spoke. And there is a lot of collaboration there. There's a lot of interest in improving the timelines so that we can get that power, we can get a pad. It's going to be an external pad that's going to come outside of the building so that we can just land modular data centers. So we're okay.
Is it unmuted?
We can hear you now.
You can hear us now? Okay.
Hello.
Thank you.
Okay. Yeah. Where do I start? Do I start here on the previous slide?
Where did she drop out?
I think it was on the slide. Oh no, it was on the last one. The last thing I heard was talking about the modular data expansion.
Okay. So it's probably the previous slide then. I can go back. All right. You guys are going to rehear me.
Thank you for letting us know.
I guess the whole thing again. So of the 80 million, 40 million generally was going to the infrastructure upgrade, and we are increasing our infrastructure at the NESC for our number 3 computer. And then we are working with GSA and a very close collaboration with GSA and AGO, because we want to make sure that the timing is right. GSA provides the pad and the power, and then I bring the compute in. So had a great meeting with the GSA leadership. We had a stakeholder leadership summit a week ago now, where Mr. Friedman and the regional commissioner of GSA spoke, and they have made agreements so that GSA can try to do things in parallel, build efficiencies in their processes so that we are able to bring the infrastructure sooner. And then I'm working at the same time with AGO so that we can award those task orders sooner and then land the compute on the concrete that we're working on. Okay, next slide. So IRA. IRA is going to be basically of the 190 that HPC has received overall, 150 is going to be for R&D. And of those 150 million, it's broken out so that I receive funds over 5 years. And since I've not received any funds, it's probably going to be 3 or 4 years, depending on when I get them. And then we have issues with BAS to work out. Okay, so the way that is split up is 90 million is for compute, slated for compute. 38 million is going to be slated for storage and data management. 20 for software engineering and project management. And then the remaining, of course, is for W cost, close to 40 million. 38 is for W cost. And then this will actually be additional systems that we are planning to bring to the NESC, because now that we have built out that infrastructure at the NESC on a modular data center basis, this will just add back on to those, and then hopefully we don't have any facility constraints to deal with for the future. So that infrastructure really helps, not just for the BIL compute, but also for the IRA and beyond. Okay, next slide. All right. So I think I just wanted to explain how this is set up. And one of the main challenge that I see is my program gets the funding at the same time that you guys do. So science and the infrastructure, the compute or the capacity gets funds at the same time. And that's a big challenge because like I explained, I have to do all these different steps to land the systems, to provide them to you. And I'm sure you're probably already ready for it much in advance. So I would really like to encourage everyone, please document, prioritize your R&D HPC as needs. Please inform in the budget cycle, in the budget process, put it in there that your science needs X compute, X storage, all that stuff, whatever you need, put it as part of your budget process so that when our compute lands, you have that available for you. And it's not something that is a guessing game, that's a prioritization game. It's already part of the law, right? It gets done. And also, please encourage your leadership to request this in advance, because just having capacity being funded only during supplemental funds is very difficult for planning, right? So we want to make sure that there's long-term planning built in as part of a sequential increase. I would love to build additional capacity and plan for that every 3 years, 4 years, 5 years, 10 years, right? Right now, it's like a faucet opening, all the money coming in, and then it's like, okay, what's going on? That doesn't help you that much. So, right. So please inform leadership, Congress, NOAA leadership to prioritize HPC, to prioritize the projects that support it, and actually really to support me by letting me know ahead of time what you guys are plans are. What's your architecture going to look like? What's your software stack going to look like? How is your cloud going to change for the next summer? I probably need to know that now, because if I want to make sure that I have additional cloud resources for you, I need to work with contracts right now. And I work with a lot of committees, work with the allocation committee, right? Also work with the HPC board. So want to make sure everything is alignment, the planning, the strategic planning, the budget, all that works in alignment so that I can provide the resource to you when you need it. There are going to be additional slides back there. I won't go through it, but it's more for overview. What do these committees mean? And all of that. And then I'll stand back for any questions.
We'll leave the backup slides in there for when we publish it on the website, so that if there is information people want to see.
That'd be great. Thank you.
Thank you, Radhika. All right, we're quite a ways ahead of schedule, which is pretty awesome because that's really hard to manage at any form of conference. So we're going to go into the Q&A for the folks in this session, and if there's no objections, we'll do our normal 15-minute break and then start the afternoon. The second session slightly early, so we might get out of here maybe 10 or 15 minutes early to ease travel for folks.
Sounds good to me, Aaron. Start the Q&A session now. Well, I saw Jim's hand first.
Yeah, I have a question about how physics changes are coordinated. I mean, it's an example, say somebody has a really great cloud scheme and puts it in, but that maybe requires radiation or some other parts of the physics to be tuned to utilize this great new cloud scheme. How is that done?
Yeah, go ahead, Mike.
Oh, yeah, sorry, I could barely hear something. Yeah, I would say this is a great example of something that fits into this hierarchy, because you're absolutely right. You know, you've got a new, what did you say, convection scheme or?
Cloud scheme.
Cloud scheme, okay, cloud scheme. You know, that's a great example. Inherently, I think it becomes part of a convection scheme, which is, 3D, especially at high resolution. But the point is, trying to exercise some of the aspects of this hierarchy to evaluate it. So what kind of things are needed? And that was a question that was put to me. What kind of observations are needed as well? Yeah, all variables at process level, I think, cloud cover, surface fluxes, boundary layer depth, things like that. So if you've got a good scheme, you need to kind of sort out, well, how and where can we get it in? How can we get it in? And that actually then necessitates a lot of tests, because there's a lot of interactions that go on. And yeah, you're right. If you have the new cloud scheme, well, radiation is going to be affected and so on. So if you can automate some of these things, and I think use of the Common Community Physics package, developed at DTC and sharing with the community, then allows us to go from one step to another step to another step in a more efficient way than doing, one set of tests, and then I've got to do a single column test, and then I want to do something on regional, etc. Then allows you to go through those tests. So I think if you want to really have a robust finding, you want to try to execute some of these simpler steps in the hierarchy to allow you to then go into the regional, global, and coupled model, including HAFS, to then evaluate it. And before you spend a lot of compute, that's what you want to do. Sorry, kind of rambling, but I think really being robust about this testing. I'm sorry. I see Dev has his hand up.
Dev, do you have another response to the last question or a new question? Because we also have a question in the room.
Just a response to the last question, in a sense that, Mike, in terms of hierarchy, but there could also be priority. And the common features I see, something like on land would be something like NOAA-MP, which I put a comment that we need to peg that in. So what could be the priority places where you would like to peg things down, that let's fix this and then we go from there? That would be something I'll be interested in. Thanks.
Yeah, that's a really good question. How do you prioritize? I know in the end we want to have a good forecast, and so you end up tuning as you have to, and that's the coupled systems say. Yeah, but how to prioritize? I think your comment about NOAA-MP is exactly right, because the characteristics of the land are going to be different than they are with the original NOAA. I guess that's working together as a physics community for testing and evaluation. We just see what bubbles up to the top. What are the most glaring errors that we have? I know I've asked the model evaluation group at EMC, and well, more broadly, I guess, can we develop a list of top 10 or how many ever of the biggest issues that are going on in regional, global, HAFS, etc. Even what we know about the parameterizations and maintaining that, and then how we can focus our time and energy on these things. I mean, DTC visitor projects would be a great example of using such a list. But I do go on. Deb, does that help?
I'll follow up. Yes, it does. Thank you.
Yeah.
Yeah, thanks for that response. We'll take the next question in the room here.
Okay, this is Hyun-Soo Kim. This question to Maui. I am working on working with the JEDI and Orion. We had a major 2 hiccups over the years. One in the springtime, and the second one is just a couple days ago, a couple of weeks ago. So it is associated with the release of spec stack. Okay, sometimes it works, sometimes it doesn't work, like the last 2 hiccups. And then we had to really spending extensive hours to figure out what. In other words, we are in the dark. So if we have a better communication or announcement with the new release, with what is upgrades, what is obsolete, that will be very informative. And the second thing is the point of contact of the spec stack release. It's a little bit not out there, because we are AOML, not part of internal. EMC EPIC or JCSDA. So how can we get into this part of internal release?
That's a very good question. I just want to mention that Backstack is actually a collaboration between EMC, JCSDA, and EPIC, right? So the three teams have different functions. Within the context, right now we don't have a good governance on exactly how information is shared with all other UFS teams. Part of this is because Backstack wasn't, well, I think it might be approved soon, but it's not approved for operational implementations at this moment, but it will be. So there was a transition issue from HPC stack to SPAC stack as well. So can you maybe submit a very high level ticket to the UFS community GitHub discussion forum so that we can track that issue? I think that's a very good, very important issue we need to track.
Again, that GitHub is designed for internal.
No, I'm not saying the SPAC stack GitHub. I'm saying the UFS community discussion. You can just raise that as an issue that we need to look into.
Okay, so that
if I send me an email, I can ask the EPIC software.
might not be only enough for me, but some other people might experience the similar situation. I happen to.
Yeah, I think it will be of very general importance to everyone.
Yeah.
Thank you.
Yes, I have a question for Wallace and Mark. So it's nice the National Hurricane Center developing the 2D wind model. It's great. So I have a question about the overland part of, you mentioned about the wind reduction overland. So the land surface type has a resolution, really great 1 kilometer resolution, but then the model would have 5, 10 kilometer resolution. So my question is that each grid point, are you using the surface roughness from that land surface map, or you did some other integrated effective roughness?
I'm walking towards Mark right now.
Okay.
This is a good one for Mark.
Were you directing that to me or Mark?
Oh, no, for Mark DiMaria, yeah.
Got it. Okay.
And
great.
Wallace.
I have some things to say about land, but
yeah, I think it's actually relevant to the HAFS model as well. Is what do you use for representative surface roughness when you've got, say, a 10-kilometer grid cell or 5-kilometer grid cell or even 1 kilometer? There's all kinds of subscale. So what we found is that when we run the surface wind model at 1 kilometer, we have a land surface database that's appropriate for that. It's kind of averaged over a kilometer. But when we run it at 5 and 10 kilometers, we're getting this crazy aliasing. Like if you happen to hit a lake or you hit a little city. So what we had to do is we had to average the surface reduction factors over a scale that was appropriate for the particular model run and to eliminate that aliasing problem. That's why we want to go down as small as possible to retain at least some of the detail. And I'm assuming that HAFS does the same thing, make some kind of assumption.
Yeah, but you're going to county warning, so those are bigger.
Yeah, depending on the use.
Yeah, thanks. Yeah, that's actually better than using the single surface roughness. At least you're taking into account of the either upstream effects or at least you look at the integrated effects. Yeah, thank you.
Yeah, that is necessary. And we do actually look upstream when we run at a fine resolution. We look a little bit upstream for the upstream surface roughness effects as well. But on the 5 and 10 kilometers, we can't do that. You can't really go back that far.
so this becomes, effective roughness where you've accounted for, you've accounted for upstream effects.
Yeah, I have a question for AC. As your hierarchical test system, is that possible? We can, I probably contact you directly start that because we have some critical development we want to test step by step before we put into our full cup holder model. So especially like the change related to physics part?
Yeah, that's a very good question. I should point out that this isn't some kind of software package. It's basically a process, a systems engineering process, essentially. I know, Aaron comes from such a background, and he expressed that support for something like that. So yeah, we certainly can talk about it, and we certainly should talk about it, and then see what we can bring to the table. 2D is kind of notional because it's an obvious step between 1D and then going to something that's 3D. That, small domain, if you will, is a great place to do some initial testing on convection. Because you can run a 200 by 200 or 100 by 100 kilometer grid box, and then not grid box, domain, with whatever size grid boxes you need in there. But yeah, we can certainly talk about this. This is definitely where DTC working with the community fits together. It is an R2O process, and not just a single software tool that we've developed.
So I have a question for Mike and one for Radhika. For Mike, where do observations fit into your hierarchical system? In almost all physical processes, you need to evaluate it by characterization of the actual process from observations in some way.
Sure.
So how does that fit in? How do you view it would fit in? Because, in other words, in our community, we actually have the ability to go out and make observations that we then use to improve our physics processes. And I know that almost all observational programs try and collect observations, but I don't know that they think about your connection. So if you could provide your view of it, that might help us.
Yeah, you can go with some of the typical NWP kind of metrics: 2-meter temperature, 10-meter wind, 500 millibar height anomaly correlation scores, vertical profiles, and things. But those are really integrated in a combination of a lot of things working together. So maybe I'm talking about more things like surface fluxes and boundary layer depth and aerosol optical depth, and well, in any number of things that are process instead of just
we don't observe those things. That's why I'm saying.
Yeah. Well, yeah, you describe it well. I guess a lot of data mining is in order here. If you look at some of the DOE arms sites, for example, and those are over land, obviously, but you've got ocean observing programs and so on. I guess squeezing every bit of information we can out of the observations we have and seeing how that'll help assess our models. I know I'm speaking kind of generically, but we need to line everything up on the table that's observation, and then we need to look at, well, where do we need them for addressing what we think are, and then what we can diagnose as are, where our biases are lying. That comment that I made that came from Christian Jakob. So, yeah.
I'd like you to think about that. That's what I think I'd
Yeah,
say.
yeah, definitely.
Yeah. Hey, Mike,
Yeah.
this is Aaron. You and I can definitely talk later if you want. We can set up where you do one of the HFIP monthly seminars, and we can go into, part talk, part discussion if
Sure.
you
What do
want.
we need? What do we need?
We can definitely work out because we've got about 5 minutes left for the questions.
Okay.
I know Frank had another one that was going to Radhika.
Don't let me monopolize here.
Yeah, so my question for Radhika is, as we move forward, you mentioned the power draw on these HPC systems. I know from my research that GPUs use less power. GPUs are becoming very common in the high performance computing clusters. I also know from chatting with my NCAR colleagues that they are using the GPUs, and that the compilers now can, with a couple simple calls like we do for MPI, address the GPU and streamline and pipeline a lot of our processes into the GPUs. Is that part of your plan?
Yes, it is. So we currently support GPUs. It's supported at the Hera system, at the NESC location, and pretty much every new compute that I'm purchasing, there is a component for GPUs. So yes. So the latest compilers are going to be ready for that. But I do have to tell you, since I was at the supercomputing conferences talking to the vendors out there, GPUs are high demand across the country, across the world, because everybody's using them for AI work. So yes, NVIDIA is getting very rich. So had a meeting with NVIDIA, and they said their supply chain for GPUs is looking 6 to 12 months. So if you guys need GPUs, please let me know, and I'll try to put that in as early as I can. But the systems are coming up with their own stack of GPUs. And for the cloud, I know getting GPUs has been a concern. And again, trying our best to make sure to work with the vendors, make sure I've established personal relationship with the account reps at NVIDIA and others, so that we can make it happen for you.
I have follow-up for this. I think the hardware, we move to GPU, we need to consider how to move our models to GPU. I don't think we have a coordinated effort, at least for the UFS model, how to move the DICO and the physics everything to run the GPU chips. There are very scattered effort. Someone is just say, test the PPL scheme, rewrite in the GPU, but the communication, if your model is only hybrid, the communication is more costly than just running the CPU. But it's still IO very expensive, the conversion from the GPU and CPU.
If I'm understanding what you're saying, right, Punglin, we basically are going to have a pretty long lead time, not only for the hardware, but for actually getting our software to work with it.
So Tim.
One second, Frank. Maui, did you want to respond to something that was said?
No, I want to ask Radhika a question.
Go ahead.
Yeah,
Can I just respond to this first?
Oh, I'm sorry, Tim. I didn't realize you were responding. I
Yeah.
thought it was a new question. Hold on a second, Maui. Sorry.
Yeah, so just real quick response to Fanglin. So we do have a group at GFDL that is working on porting FE3 to GPUs.
Yeah, I know it's on the way.
Maui, go ahead.
okay. So my question is, Radhika, you mentioned that you have a few new hires to help with cloud porting. What would be the best way to reach out to them?
So Maui, right now we are going to be coming up with a process on making sure that we understand the requirements of what is needed, because I know Epic is also doing some efforts with supporting the users on UFS. I'm bringing on a team to help with the porting to cloud and other systems. So I think I need to understand from the user community the issues they've been facing with porting. So, and then on my side, I'm going to line up the capabilities and the expertise necessary for those specific projects. So I have the team, and I think it's just a matter of lining up what are the issues and who's going to be supporting on what project across all the systems. So I think it's just trying to understand what exactly the issues the users are facing at this point, and then moving on to doing a matching.
So a follow-up question: do you view Epic as a user in this context?
Well, sure. I think we can have discussions, and then we can work to come up, how it's gonna support you, right? So
That's great.
And I know you are also supporting your users, so it's kind of like we're gonna have to plan this out so that we're not stepping on different boundaries there.
That sounds great. That means we might need to have a conversation about this, right? So that we don't duplicate the efforts.
That's great. That's great. Thank you. Yeah, we should have a follow-up.
Yeah, thank you.
All right. We're going to have one more comment question from Shujin, and then we're going to take our break and be back about 10:45, and we'll get started a few minutes early on the last session of the day.
Yeah, so when you plan the HPC acquisition, I think it also considers how much software and training put into that acquisition, because right now most of scientists still write code based on CPU, and when we transition to GPU, I like use a lot of our technology on GPU, because that's one of the direction we're going to go. But when you do this, consider a lot of the software plus the training for the, left some money for that. Don't buy all the hardware, because if the hardware sits there, burn your money. Meantime, have the life's expensive. If you have the machine sit there 1 year, cost you a lot of money, and we'll waste a lot of resource on that. So make sure that by that meantime, let's scientists also ready, our engineer ready to use that.
So it's last year's cloud problem all over again. We have allocations sitting and nobody touching it, basically, at that point, because they're not capable or experienced enough, I guess, is what Shujin's getting at.
Oh, no, I think it's the community involvement, right? So I think everybody needs to have that. So I think that's the common software. So I've always been asking, okay, provide me with the common architectures, the software platforms, so that I could run my systems and do some benchmark testing for you using those applications, so that the system can support those applications, right? So I guess from my perspective, it kind of, before the system comes on, it kind of goes back to that, provide me with the architecture, the applications, the software stack that you want to need to make sure that the system can support you. Right. I'm sure the scientists need time to adapt to the new way of writing it. Right. I understand. Okay. Yeah.
All right. Thank you, everybody. We're going to take our break, be back at about 10:45 Eastern time. Thank you.